Okay, for anybody that joined us a little bit late, Nur Yazdani was going to be here to moderate this session and also to do this presentation. He emailed me on Friday. He was ill and not able to make it to ACI, so I volunteered to moderate the session and also do his presentation for you. It was Nur's work and not mine, so I can certainly relay questions to him. So the outline for the presentation, I'll talk about an introduction, the problem statement, what is it he was trying to solve, his research objectives, descriptions of the bridge that were tested, some ambient vibration tests, dynamic load test, finite element model calibration, retrofitting, and then finally the conclusions. The American Association of State Highway Officials, AASHTO 2020, only imposes a deflection limit that is insufficient to counteract vibration. In addition, a dynamic impact factor defined by the dynamic to static response ratio is used to amplify the live load without considering the vibration severity of the individual bridge. Furthermore, it's been established that vibration severity, quantified by the peak acceleration of highway bridge components during regular traffic flow, is the most significant parameter affecting the deck, cracking, and for long-span bridges. The current condition of highway bridges can be assessed by obtaining the dynamic properties such as acceleration, natural frequencies, and mode shapes. So here's our problem statement. You have this bridge over Wilson Creek in McKinney, Texas. Observed to have progressive cracking, localized potholes on the deck. Excessive vibration was felt on the deck when heavy traffic passed over the bridge. And the UTA team initially visited the bridge site on January 29, 2018, together with personnel from TxDOT. Being built in 2011, it was unusual for the bridge to experience such issues. So it's a 7-year-old bridge, wow. Right? All right. A diagnostic load test combined with non-destructive evaluation on the bridge revealed considerable delamination at the deck-girder interface. In addition, a significant shift to the neutral axis from the theoretical full composite location was observed, indicating a loss of composite action at the deck-girder and cast-in-place PCP interface. A follow-up load test on the bridge after a year showed nonlinear strain response and only 59% composite action for the girder deck system. The delamination and partial composite action compromised the stiffness of the superstructure and induced excessive vibrations. Further information regarding the combined load test and NDE evaluation of the test bridge may be accessed from the literature. The current research investigated the effect of partial composite action and deck delamination on the dynamic properties of the test bridge. In addition, various retrofitting methods to mitigate vibration, partial composite action, and delamination were studied. Therefore, this study could be a benchmark for future studies and dynamic evaluation and retrofitting of partial composite action induced vibration of prestressed concrete girder bridges. Its specific objectives are, number one, to conduct an ambient vibration test on the subject bridge to measure the superstructure component's maximum acceleration in the vertical and lateral directions. Number two, conduct an ambient vibration test on 2 other similar reference bridges with no signs of a significant vibration issue to compare the maximum acceleration with the test bridge. And number 3, obtain the natural frequency and mode shapes of the IM of the test bridge by conducting dynamic tests. Number 4, model a representative girder with an effective deck width of the test bridge in Abacus CIE and calibrate it using the load test data. And finally, number 5, apply practical and cost-effective stiffening methods on the calibrated model to mitigate the vibration. So the bridge was built in 2011, State Highway 75, SH-75 bridge over Wilson Creek in McKinney, Texas, has both northbound and southbound bridges. It has 4 spans, and each span includes 11 Texas Department of Transportation standard TX54 prestressed I-girders with a spacing ranging from 2.74 to 2.9 meters. The deck, consisting of a composite cast-in-place deck on a precast prestressed concrete panel, is 29.87 meters wide out to out and 216 millimeters thick. An ambient vibration test under regular traffic was conducted on the SH-75 over Wilson Creek southbound bridge to obtain the acceleration of the girders in the deck. To provide a comparative analysis, a similar test was conducted on 2 control bridges with no vibration issue, namely northbound SH-75 over Wilson Creek and northbound SH-75 over Virginia Parkway, bridges in McKinney, Texas. The control bridges are similar to the test bridge since both were made of cast-in-place decks on partial depth concrete panels on TX54 girders. Vibration data were collected from the bottom of the girders and some portion of the deck for all of the test bridges. Additionally, some bent caps and bearing pads were also instrumented. The ambient vibration testing plans for the 3 bridges are shown in the figure. The data collection at each location involved taking readings for 15 minutes at a rate of 100 data per second using a vibration meter. All the tests were conducted from 4 to 6 p.m. to capture the effect of heavy traffic on the vibration parameters. The figure shows typical vibration meter locations on the southbound Wilson Creek Bridge. The maximum transverse acceleration of the southbound Wilson Creek Bridge girders was 145% and 86% higher than the northbound Wilson Creek and the northbound Virginia Parkway bridges, respectively. Similarly, the maximum vertical acceleration for the southbound Wilson Creek Bridge was 140% and 40% higher than the northbound Wilson Creek and northbound Virginia Parkway bridges, respectively. The excessively high acceleration of the southbound Wilson Creek Bridge superstructure indicated reduced stiffness of the deck-girder system, confirming the findings of the previously conducted NDE and load test. Therefore, the progressive transverse and longitudinal cracks, potholes, and excessive vibration on the bridge were due to the reduced stiffness of the delaminated and partially composite deck. The spans beginning, middle, and end, and the paths for the truck runs were marked on the day of the load testing. The figure shows the different load paths. The truck started before bent 4 and stopped when it exited bent 3. The girder with maximum impact for a particular load path was instrumented with a vibration data logger during each of the load tests, as shown in the figure. The midspan of girder 1 was instrumented for load path P1 since it experienced the maximum impact in its path. Similarly, girder 4 and 8 midspan were instrumented for paths P2 and P3, respectively. Additionally, the midspan of the deck between the girders 3 and 4 was instrumented for path P2 to evaluate the deck response. The natural frequency of the southbound Wilson Creek Bridge was extracted from the dynamic vibration data by applying a fast Fourier transform. FFT was applied to the ambient window data to convert the time domain data into the frequency domain and separate the individual frequencies and amplitudes of the signals. However, the experimental natural frequency was 2.03 Hz, which was very low compared to the values of literature due to the development of cracks and decreases in the stiffness of the deck-girder system. The severe delamination of the deck and the partial composite action in the girders deck system reduced the superstructure stiffness significantly, resulting in high accelerations and low fundamental frequencies. To save computational costs, a single girder with a composite deck instead of the entire span of the southbound Wilson Creek Bridge was modeled in Abacus. The model was initially calibrated employing the field test data reported to capture the in situ behavior of the bridge. The girder was modeled using solid three-dimensional deformable elements, while the embedded reinforcements used two-dimensional truss elements. A 127 millimeter native mesh size was used for all the model components. The compressive and tensile behavior of the damaged plastic CDP model, a bilinear strain hardening model with two different slopes was used to approximate the nonlinear stress-strain relationship of the mild steel. The stress-strain relationships of the low relaxation prestressed strands were modeled using the PCI 2021 approximation. In plane stiffness KSS and out of plane KTT cohesive contact shear stiffness of 103 megapascals was assigned to the girder deck interface to introduce partial composite action. This value was obtained after calibration of the model employing the static load test results reported in the literature. The normal stiffness coefficient, KNN, was assigned a constant large value of 6,895 gigapascals, since only shear failure between the interfaces were modeled to introduce partial composite action. A dynamic frequency step was created in the model with the first 10 eigenvalues after the general static step. The dynamic model calibration involved varying the stiffness of the deck between 100 and 60%, since the load testing and the NDE results confirmed severe delamination and reduction in the stiffness of the deck panel system. With 60% remaining stiffness of the deck, the model frequencies agreed well with the experimental results with minimal deviation. So retrofitting with shear keys. Concrete shear keys that are 38 centimeters along the longitudinal direction of the girder were proposed between the bottom flanges of the girders to reduce the lateral movement of the superstructure. This figure shows the cross-section of the superstructure and the bent cap with shear keys. This option does not cause traffic interruptions under the bridge since there is adequate construction space outside the travel lanes. The shear keys were applied at the girder ends of the calibrated model at 38 centimeter lateral fixity. It can be observed that the shear keys increase the natural frequencies from 2.41 to 3.11 hertz, or by 29%. However, according to Aman, the minimum natural frequency for the southbound Wilson Creek Bridge should be 3.28 hertz. Therefore, installing shear keys alone will not provide enough lateral stiffness to the superstructure to mitigate the vibrations issues completely. So retrofitting with dense concrete overlay, the impact echo data revealed considerable bridge deck delamination, mostly within 102 millimeter depth. So two models with 51, so half depth, and 102 millimeter full depth delaminated concrete removed from the top of the deck and then recasted with dense concrete overlay were developed. In addition, two models combining shear keys between the girders with the dense concrete overlay atop the deck were developed. So as seen in the table, the dense concrete overlay improved the stiffness and removed the delamination, resulting in an 18% increase in the natural frequencies. Furthermore, the dense concrete overlay combined with shear keys significantly increased the natural frequency by almost 50%. The 51 millimeter overlay combined with the shear keys increased the natural frequency to 3.36 hertz, higher than the 3.28 hertz minimum value per the previous study. Therefore, a 51 millimeter overlay combined with the shear keys is the optimum solution to mitigate the excessive vibration on the southbound Wilson Creek Bridge. So due to the 127 millimeter embedment in the decks, a 381 by 381 millimeter rectangular area at the deck-girder interface was assigned a tie constraint to ensure a perfect bond at each anchor location. For the remaining bridge area, girder-deck interaction was assigned cohesive contact. The figure shows the tie areas in red blocks between the deck-girder interface, indicating the tension cones of the undercut anchors. The modeling considered 20, 40, 60, and 80 anchors. In addition, shear keys were modeled with the anchors to monitor the combined effect. So this table compares the natural frequency of the calibrated and retrofitted models. Undercut anchors increase the stiffness of the system by improving the composite action between the girder and the deck panel system. It can be observed that even by installing 80 anchors on each side of the the top flange, the natural frequency is 3.13 hertz, which is still below the 3.28 hertz minimum value per the literature. However, 40 anchors on each side of the top flange combined with the shear keys mitigate the excessive vibration and increase the natural frequency by 60%. Since the impact echo data showed the prevalent delamination on the girder lines, the deck on 2/3 of the top flange width of the girder, 0.61 meter wide strips, was removed and recast to improve the composite action and increase the system's stiffness. High and regular strength concrete with compressive strengths of 41.4 and 27.6 megapascals respectively were used. Similarly, 0.30 meter strips were removed along the panel lines and recast with the same type of concrete. The existing bridge deck was made of concrete with a compressive strength of 28 megapascals. It was assumed that the new concrete bonds perfectly with the deck and the girders, thus tied contacts were defined between the surfaces. Additional shear keys were modeled, combined with this retrofitting to evaluate the combined effect. Recasting the girder and panel lines with high-strength concrete improved the natural frequency by 25%, but it's still below the minimum value of the 3.28s in the literature. However, combined with the shear keys, it improved the natural frequencies by 41% and 45% for regular and high-strength concrete retrofitting, respectively. In addition, it yielded a natural frequency above the minimum limit of 3.28 hertz. Therefore, shear keys combined with the recasting of the girder and panel lines with regular strength concrete suffice to mitigate the excessive vibration. So, a retrofitting cost analysis, it can be observed that the shear key is the most cost-effective and does not require any traffic closure. Since shear keys are cheap, they can effectively be incorporated with other stiffening methods. Dense concrete overlay is an expensive option and requires extensive traffic closure atop the bridge. Undercut anchors is the costliest method since drilling and installing require highly skilled labor. Recasting on the girder and panel lines is cheaper than dense concrete overlay and undercut anchors requiring only moderate traffic closure on the top. And finally, the conclusions, the maximum accelerations of the girders and the transverse direction under regular rush hour traffic were significantly higher for the test bridge than the other two comparable bridges. The fundamental frequency of the test bridge was significantly lower than the acceptable frequency mentioned in the literature. The reduced stiffness due to partial composite action was the reason behind lower fundamental frequencies and higher accelerations. Shear keys by themselves or combined with other methods significantly improved the system's natural frequencies. A dense concrete overlay reduced the top delamination of the deck. Undercut anchors directly increased the composite action and stiffness of the system based on the number of anchors. And recasting of the girder lines and panel lines improved the composite action and reduced the lamination on the deck. Thank you to Nur for his presentation.